Okay, anybody have any questions from last time? So we started talking about units and measurements, and I said that there are 4 basic unit types. 4 basic, we'll call them quantities, that all the other quantities are made up of. So it's length, time, mass, and those are the ones that are going to matter in this class. And then there's the 4th one that's charge. If you take Physics 2, that's going to come up, but that won't come up in this class. We are going to use almost always SI units. So we'll mostly use SI units. That's for Standard International. And so for us, length is going to be meters, and we'll abbreviate that lowercase m. Quantities of time are going to be seconds, so that's lowercase s. And masses are going to be measured in kilograms, and that's kg. When you're given a value for like something that you've measured, so think of a measured quantity as a number times a unit type. So a number times the unit. So for example, 56.3 meters. Think of that as the number 56.3 times this thing that times this length of 1 meter. So this 56.3 meters, you can just think of that as that m as being like an algebraic variable, and you're just multiplying a number by it. So you can treat the unit as an algebraic variable. That lets you cancel units. So for example, if you have 10 meters times seconds, I don't know what meters times seconds would be measuring, but you could come up with a measurement that uses units of meters, meters times seconds, and you divide by 5 meters. Since you're thinking of this as a 10 times an m times an s, and you're just treating those just like any algebraic variables, you can cancel the meters, and your final answer here is just 2 seconds. So all of our unit conversions are going to be based on thinking of it that way. So now unit conversions. A lot of times we're going to want to know how much of one you know, so there are all these different measures of any individual quantity. There's all these ways to measure length. You can do it in light years or meters or inches. And a lot of times we'll want to know how much of one of those is, you know, a quantity of another one. So for example, how many inches are in 3.5 feet? The way we're going to deal with this is we're going to always take this starting quantity, 3.5 feet, and multiply it by something that's equivalent to 1. So we're not going to change it. You know, anything you multiply by 1, it doesn't change. But we know that 1 foot is equal to 12 inches. So that means that 1 foot over 12 inches is equivalent to 12 inches over 1 foot. And these are both just sort of ways of expressing the number 1. The numerator and denominator are the same thing, so either one of those is equal to 1. And so we can multiply either one of these two fractions by anything we want without changing the value of this thing. We're just re-expressing it. So we'll multiply the original quantity by 1. In this case, we'll start with 3.5 feet. And we'll multiply it by 12 inches over 1 foot. Since we're multiplying 3.5 feet by 1, we haven't changed the quantity that we have. We're just re-expressing it in new units. These feet cancel out, and you come up with 42 inches. Any questions about that, like, basic idea? So these equivalences that we're going to always have between, you know, a mile is equal to this many meters and an hour is equal to this many seconds, those equivalents are going to give us ratios that are equal to 1. And we're going to multiply our original thing by those ratios that are equal to 1. What if I'd multiplied by the other fraction? These are both equal to 1. So it should be fine. What if I'd multiplied by 1 foot over 12 inches? Right, that should be fine. It shouldn't change the value of what we have. So 3.5 feet, and then multiplied that by 1 foot over 12 inches. Well, it gives us this, you know, nothing cancels here, and so we end up with 3.5 over 12 is like 0.2916 repeating. And the units we get are feet times feet over inches, so feet squared over inches. And it's not wrong. This is a valid unit of length. You could use that. And this is the correct length. This is a length that's equivalent to 3.5 feet expressed in this funny set of units. It just isn't the set of units that I asked for. It isn't the one we want. So how do we know which, you always have these two choices for ratios to multiply by. How do you know which one is the one you want? So let me just say that's correct. But it's not the units of length that we want. So what you want to do is you always want to multiply by the ratio that makes the unwanted units cancel. Okay? So always choose the ratio. And remember, each of these ratios is like a version of the number 1. That cancels the unwanted units. So how can we tell the difference between the way we wanted to do it, this first approach, and the second approach that didn't give us what we were looking for? Well, we started out in units of feet. Those are unwanted units. We want units of inches. So we need to multiply by the ratio that cancels the feet here. Okay, so we need the feet to be on the bottom because in our original quantity, the feet are in the numerator. Okay. Any questions about that idea? In this case, our unwanted units were feet. We multiplied by a ratio that didn't cancel the feet. And so we ended up with this thing that still represents the same length, but it's not the one that, it's not what we asked for. Okay, so let me do a couple examples. How many days is 46,000 seconds? So we're going to do it two ways. First, we're going to use the fact that 1 day is 86,400 seconds. And then the second way we're going to do it is, so did anybody know this off the top of your head? Well, actually, I'm sure you didn't because actually, I think a day is supposed to be 24 hours and 24 hours and 15 minutes or something, and I didn't include the 15 minutes, so this is wrong. But this will give you the idea of how to do this anyways. So, okay. Nobody remembers that a day is 86,400 seconds, but you do remember that 60 seconds is 1 hour. 1 minute. Thank you. I'm just making sure you're paying attention. 60 seconds is 1 minute, and 60 minutes is 1 hour, and 24 hours is a day. And you remember all of those. I don't, but you do. So the first approach, we're going to start with our original value, 46,000 seconds, and we're going to multiply it by either 1 day over 86,400 seconds or by 86,400 seconds over 1 day. Which of those two do we want? Or do we want the 46,000 seconds on top or bottom? Yeah, we want it on the bottom so it cancels the seconds here that are on top. So 1 day is on top, 86,400 seconds is on the bottom. I'm going to use a shorthand to write this. I think it's probably everyone who's taken chemistry here has used this same shorthand. Instead of writing out all these parentheses, I'm going to write it as 46,000 seconds. There's the division line. And the things that are in parentheses, I'm just going to separate with vertical lines. So 1 day, 86,400 seconds. And then you can see the seconds, the unwanted units cancel. And you get about 0.5324 days. Okay, so now let's do it in the sort of roundabout way where we don't know directly the conversion between seconds and days, but we know how to get from seconds to minutes, minutes to hours, hours to days. Okay? And what we're going to do is just sort of step by step multiply our original value by ratios that are equal to 1 to convert first to minutes, then to hours, then to days. Okay? So we'll start with 46,000 seconds. We'll use this first relationship to convert from seconds to minutes. So we're either going to have 60 seconds over 1 minute or 1 minute over 60 seconds. Where do we want the seconds to be? Top or bottom? Bottom. So we have 60 seconds, 1 minute. And I'll cancel those right now. You can see that if we multiplied this out, now we'd be in minutes. And now for the second step, our minutes are the unwanted units. And we want to go to hours. So I'm going to multiply by either 60 minutes over 1 hour or 1 hour over 60 minutes. Do we want the minutes on the top or the bottom? Bottom again. So 60 minutes, 1 hour, and then those cancel, and if we multiplied out these numbers, we'd have that original amount of time represented in hours. And then the last one, 24 hours over 1 day, or 1 day over 24 hours. Where do we want the hours? Bottom. And the hours cancel. And now the only units we have left are days. And if you multiply all this out, hopefully you get the same thing. That would be really unconvincing if that wasn't true. I'm going to assume it's true. So 46,000 divided by 60, divided by 60, divided by 24 gives you the same answer we got the first way. Any questions about that? Okay, so this is like as simple as this can be because these are all these units are just a single quantity, a single type of unit. But you can have measurable quantities that are combinations of units, like miles per hour or meters per second squared. And so converting those, takes a few more steps. So let's do one where we have a combination of units and we have to convert it to a different combination of units. So how many meters per second is 61 miles per hour? Our original measurement is 61 miles per hour means miles on top and hours in the denominator. Oh, and I need to give you some values before you can do this. 1 meter is equal to 3.281 feet. Uh, 1 yard. Why am I doing it like this? This is a crazy way to do it. Yeah, well, I think my original plan was, oh yeah, that's a different one. That's a different problem. Okay, so let's just go 1 meter, no, let's go 1 mile is equal to 1,609.344 meters. And then 1 hour is 3,600 seconds. Okay, so anybody who ran the supposed mile in track, you ran that short of a mile. That's there was a kid from Burnsville in like 2000. What would it be? 2008, I think. Question? Or were you like, I was that kid? But there was a kid at Burnsville High School in 2008 who ran the high school version of the mile under 4 minutes. But if you account for the fact that he was 9.344 meters short, he really ran like a mile in 4 minutes. So only I think in the whole history of high school track, there have been like 7 or something high school kids who've run a 4-minute mile. So it would have put him in this like super famous group of superstars. But when you added on when you took into account that he was 9.344 meters short, it was like 4 flat point 2.6 or something. You know what I mean? So sad. Okay, so what we're going to do is we're going to first use a ratio that converts miles to meters, and then we're going to multiply by another ratio that converts hours to seconds. So the first ratio is going to be 1 over 1609 or 1609 over 1. Do we want the miles in the numerator or denominator? In the bottom. So 1 mile is 1609.344 meters. And so if you cancel, you can see that now we've taken care of the length. We have the right units for length. But if we multiplied the numbers right now, we'd have units of meters per hour. We want meters per second. So now I'm going to multiply by 1 over 3,600 or 3,600 over 1. Do we want the hours in the top or the bottom of this ratio? This time we want it in the top, so it'll cancel the hours that are in the bottom. So 1 hour is 3,600 seconds. So those cancel. The units that are left are meters per second. And if you multiply and divide out those numbers, you get 27.26 meters per second. And so the difference between, something measured in meters per second compared to miles per hour, you take the meters per second and multiply by, I think it's like 2.24. That ratio always holds, Whatever 61 is divided by 27.26, that's always the ratio of meters per second of miles per hour. Okay. Now let's do another type. Something that happens pretty often is that the quantity that you're measuring has some of these base units to a power, squared or cubed or something like that. And so let's do one where we have to do that. So let's say we want to convert 9.81 meters per second squared into units of yards per minute squared. And let's say that the conversions that we're given are 1 meter is equal to 3.281 feet. One yard is equal to 3 feet. And 1 minute is 60 seconds. Okay, so I'm going to start by writing our original quantity as 9.81 times meters divided by seconds squared. And the seconds squared I'm going to break up into seconds times seconds. And the first thing I'm going to do is convert meters to yards. And the way we're going to do that is to go from meters to feet and then feet to yards. So to go from meters to feet, we're going to say 1 meter is equal to 3.281 feet. So those meters cancel, and if we multiplied out the numbers, now we'd be in feet. And now we want to go from feet to yards. So 3 feet in the denominator is equal to 1 yard in the numerator. The feet cancel. And now we're done with the conversion of meters to yards, but we still have, our time units are still seconds, and we want to change those to minutes. The seconds are in the denominator, so in our ratio, we want the seconds to be in the numerator. The ratio we're going to use then is 60 seconds over 1 minute. So and if you cancel those, you can see that we're kind of at this halfway point. We've converted one of, we started with seconds times seconds. Right now we've only converted one of those seconds to minutes. So if we multiplied out these numbers, our units would be yards per seconds times minutes, And so we have to do it one more time. So 60 seconds over 1 minute. So that cancels. And now our units are yards per minute squared. And if you multiply that out, you get a big number, 38,640 yards per minute squared. By the way, units of length per time squared are the units of acceleration. And that quantity that I started with, 9.81 meters per second squared, is the downward acceleration of an object in free fall. And when I say free fall, I'm not distinguishing between something that's just falling straight down or something that's in projectile motion. So like when you shoot a bullet, that's also in free fall. So projectile motion too. Yep.
You have the wrong figure. Just because I've done it multiple times.
Mm-hmm.
I keep getting 38,623.
Oh, really?
Yeah.
That's weird.
Like I
Okay.
did it like 5 times. I thought it was going crazy.
I wonder. You know what? I'll bet I did. I'll bet I 23. I don't know. I probably just
24 if you round it.
rounded something. Thank you. Okay. Okay, let's do one more example. And actually, I'll write this up here, and why don't you see if you can think through this problem. So let's say that you have a box so it's a cube, all the lengths are the same. And let's say that all the lengths are 1 meter. And this box is made up of, it's actually a stack of centimeter cubes. You know, so there's just level after level of little cubes where the lengths are a centimeter. How many little cubes? So that's 1 centimeter lengths. Are in the big cube, given that there are 100 centimeters in 1 meter. Okay, so take a couple minutes and see if you can reason that one out. Okay, so to do this as a conversion problem, you have to think of the volume of this cube. And the volume of this cube is 1 meter cubed. And we want to convert that to units of centimeters cubed. So I'm going to start with the quantity 1 meter, meter, meter. And then just one by one, I'm going to convert these 3 meters to centimeters. So 1 meter is equal to 100 centimeters. Centimeters on top, 1 meter on the bottom. And one more time. And you get 1 million, which is kind of amazing. That's all. A million is a big number, but that's like, you can actually picture that. Like, this table's about a meter this way, and so, you know, a meter is this, and then a meter high. So that cube off the table, you know, and a centimeter cube isn't that tiny, like it's this big. But inside that big cube is 1,000,000 of those little centimeter cubes. Any questions about that?
Can we close the doors?
Yeah. That's not really a question about that.
No.
Okay. All right, so that's about it for converting units. So let's talk about scientific notation. And so the idea of scientific notation is that any number can be expressed as one non-zero digit and then a decimal point, and then a decimal that can have as many figures as you need for the precision that you need, times 10 to some integer. For example, negative 3461.45 can be written as negative 3.46145 times 10 to the third. And 0.000, how many zeros did I make here? 0000, 4 zeros, 815. Can be written as 8.15 times 10 to the 1, 2, 3, 4, minus 5. One thing to notice here is that you never have to fiddle with the sign. So the sign is always the same, whether you're using standard notation or scientific notation. One nice thing about scientific notation is that scientific notation makes it easy to figure out how many significant figures a number has. All of the digits before the times 10 to the n, are significant. So you just count them up. So like, for example, these two numbers that I put up here, we have 1, 2, 3, 4, 5, 6 significant figures for the first one, because you're just adding, just counting up those numbers. And for the second one, we have 1, 2, 3 significant figures. And I don't know if I think most people in this class have probably had another class where you talked about significant figures. And if you're using standard notation, there's kind of a lot of rules for how to determine how many significant figures you have. Like look at this second one. It's like, okay, zeros sometimes count as significant figures if they count if they're after the decimal, but they don't count if they're before the decimal unless there's a decimal. Like it gets sort of complicated. With scientific notation, it's just immediate and clear, so that's a nice thing about it. And that is the beginning and end of everything I'm going to say about significant figures in this class. I don't care about them in the least. And because I figure, like, for the people who need them, you'll have to take other classes where they talk about them. And for the people who don't take other classes that talk about them, they won't need them, so I'm skipping it. I'm just depending on the chemistry teachers and stuff, thinking it's a big deal. Okay, so there are two things that we need to be able to do with scientific notation. We need to be able to go from standard notation to scientific notation, and we need to be able to go from scientific notation back to standard notation. So we want to be able to go back and forth . My sister-in-law, my brother's wife, she teaches like biology and chemistry, and we were talking about this, and she was just like just couldn't believe my cavalier attitude about about significant figures. She was just like all upset, and I was like, I'm so happy that you feel that way, because like that just makes me feel safer about not ever talking about it, because they're going to have people like you. Okay, so we want to be able to go back and forth between standard and scientific notation. Okay, so first, if you are given a number in standard notation and you want to express it in scientific notation, so to put a standard number in scientific notation, and I'm going to go through an example as I do this. So let's say the number is negative 541.6. Okay, so the first thing that you need to do is count the number of places n that the decimal point has to move to give one non-zero leading digit. And did you have to move the decimal point left or right? So in this example, how many places do you have to move the decimal point for one leading digit? 2, and you have to move the decimal point to the left or the right? Yeah, so in this case, n is equal to 2, and we had to move it to the left. And then if you moved it left, then you're going to have times 10 to the positive n. And if you moved it right, you'll have times 10 to the minus n. So in the example that we did, negative 541.6, we'll have negative 5.416 times 10 to the positive 2. I didn't mention this before, but if you've done a lot of this and you have an approach that works for you, keep doing it. I don't care how you do this, but you are going to have to go back and forth between standard notation and scientific notation. So if you're not already comfortable with this, this is an approach that'll work. Any questions about that? Okay, so then the second thing that you'll have to do is put a number in scientific notation into standard notation. And the example I'm going to use is 6.52 times 10 to the minus 4. So we're going to take that number and express it in standard notation. Okay, so the first step is read the absolute value n of the exponent and figure out whether doesn't take much figuring out. Remember, whether the exponent is negative or positive. So in this example, n is equal to 4, and it's negative. If the exponent is positive, move the decimal point n places to the right. If the exponent is negative, move the decimal point n places to the left. So in this example, we have 6, 5, 2. The original place for the decimal point is, right after the 6. Our exponent is negative, so we're going to go to the left 4 places. So 1, 2, 3, 4. So there's the decimal point. all of these spots have to be filled with zeros. And so there's the number in standard notation. Any questions about that? Okay. Probably the most useful place for scientific notation is numbers that are really, really big and numbers that are really, really small. So this is just something to keep in mind. Notice that you should be careful about using standard notation with, well, I guess the thing that I want to emphasize here is the very small numbers, tiny numbers. For example, say that we have this number 0.0000872. It's such a small thing, it seems like it might be reasonable to round this off as point, how many did I put? 1, 2, 3, 4, 5. 0.000009, right? I mean, that's more decimal places than you almost ever write anyways. So it's kind of natural to think like, well, I'm keeping more decimal places than I normally would. That should be good. But if you multiply or divide by this number, it turns out you're throwing away a lot of precision in your answer. If you're adding or subtracting, then that intuition is fine. But multiplying and dividing, you can get really big round-off errors by doing this. But it causes problems with multiplying or dividing. So instead, use scientific notation for this and write it as 8.72 times 10 to the 1, 2, 3, 4, 5, 6, minus 6. So notice that this one, if you wrote this rounded version in scientific notation, this would be, you'd be writing it as 9 times 10 to the minus 6. And when you look at these two compared to each other, it's sort of more obvious that you're throwing away a lot of precision if you use standard notation and do that rounding. Okay, so just be careful with that. That really, so I said I wasn't going to talk anymore about significant figures, but that's really a significant figures issue. You're given a number with 3 significant figures, and if you do that rounding, you're cutting it down to 1 significant figure. Any questions about that? Okay, the last thing that I want to talk about with units and stuff is prefixes. And I'm just going to give you a list of the most common ones. The prefixes I'm going to talk about are micro, milli, centi, kilo, and mega. And these all have abbreviations. Micro is the Greek letter mu, sort of like halfway between an M and a U. Milli is a lowercase m. Centi is lowercase c. Kilo is lowercase k. And mega is an uppercase m. And the way to deal with these is to just think of these prefixes as being equal to times 10 to the minus 6 times, for micro, for milli, times 10 to the minus third, for centi, times 10 to the minus 2, for kilo, times 10 to the positive third, and for mega, times 10 to the positive 6. And so wherever you see one of these prefixes, get rid of the prefix and just replace it with this number, multiply it by this number. So for example, 50 kilometers is equal to 50 times 10 to the third meters. 10 microseconds is equal to 10 times 10 to the minus 6 seconds. And you can also, there are times when you also need to use these ratios the same way we did with other unit conversions. So for example, 1 microsecond is equal to 1 times 10 to the minus 6 seconds. So 1 microsecond over 1 times 10 to the minus 6 seconds is equal to 1 times 10 to the minus 6 seconds over 1 microsecond. And those are both equal to 1. Okay, so you can use this same idea to come up with those ratios that you use to convert from, one prefix to another one. Okay, so here's an example of doing that. Let's say we want to know how many kilograms is 50,000 megagrams. I've never really heard the word megagram, but so we're going to start with 50,000 megagrams, and I'm going to just right off the bat replace that with, so the big M is equivalent to times 10 to the 6th, so I'm going to write this as 50,000 times 10 to the 6 grams. And then I'm going to use the relationship between grams and kilograms. So for this, I'm going to recognize that 1 kilogram is equal to 1 times 10 to the third grams. And so for the conversion, I'm going to write 1 times 10 to the third grams on the bottom, 1 kilogram on the top. The grams cancel. And you end up with 50,000 times 10 to the third kilograms, which is, in scientific notation, that's 5.0 with whatever number of significant figures you want to claim for that, times 10 to the 7th kilograms. Okay, let me do one more example. The fastest that anything can move is the speed of light. Nothing moves faster than the speed of light. And the speed of light is abbreviated c, and it's equal to .00 times 10 to the 8th meters per second. So the question is, can anything move at 150 kilometers per microsecond? So we're just going to re-express 150 kilometers per microsecond in meters per second, and then we can compare those numbers. So 150 kilometers, I'm going to write that as times 10 to the third meters. And then in the denominator, we have, you can think of that as 1 microsecond, so that's 1 times 10 to the minus 6 seconds. Now our units are meters per second, so this is 150 times 10 to the 9th meters per second. That's faster than 3 times 10 to the 8th meters per second, so it's not possible. Yep. That's just, so if I just wrote it as 3, that would indicate that that is a significant figures thing. That would indicate that we know it's not 2 and we know it's not 4, but it could be 2.6 or 3.4 or something. This is saying we know it's not 3.01 or 2.99. So it just tells us how pinched in on that value we can assume it is.
Will you switch back and forth between writing out 10 to the whatever versus e to the 8?
Did I write E? Oh, yes, I will. Actually, I'm probably going to end up writing it like this most of the time. That was an accident there, though. That's another thing chemistry teachers freak out about. Chemistry teachers. Don't get me started. Okay. Anybody have any other questions about that? All right. Well, let me just introduce the next topic. We're not going to go into anything with it, but let me just sort of point out what's coming on Monday. Oh, before I do that, so now we're ready to do all the problems for the in that first set of practice problems. So I'll put that in D2L, but you should get to work as soon as you can on the practice problems for measurements and units. And the next topic we're going to get into is kinematics of a particle along a line. So this is a new topic. Along a line is pretty straightforward, but we have to be clear about what I mean by a particle and by what I mean by kinematics. So kinematics means that all we're doing is describing motion. We're giving relationships between quantities that you could measure from a videotape. Okay? A videotape is something we used to use before you were born. Yeah. So this is just describing motion. It doesn't go into what causes motion or anything like that. It's just quantities that describe the motion that's happening. No causes of the motion. So all kinematic quantities could be measured from a video. So we'll be talking about position, velocity, acceleration, and time. What we won't be getting into in kinematics is force or mass or energy or momentum. That's not true. Force, energy, and mass. Okay. And just to make things complicated, when you do include forces and energy and mass, that's called kinetics, which is like really unnecessarily close to kinematics. You know, I don't know why they did that, but I don't get to change that. And then a particle is an object that we treat, so an object that's treated as having no length dimensions. You can think of it as like, we treat it like it's a point moving around in space. And because of that, if something has no length dimensions, there's no way to differentiate between the top and bottom or left and right. And so when you're dealing with particles, you don't care at all about the object's orientation. We only care about its location. So we only care about its location not its orientation. After we're done with this, in a couple weeks, we'll be talking about motion of particles in two-dimensional space. And so a particle that's moving in two-dimensional space, it can do all this. But we're going to start by just talking about the tracking of a particle as it moves along a line. Okay, so we won't have to worry about it turning or anything. All we're going to have to worry about is it speeding up, slowing down, you know. All right. Anybody happen to have any questions about that? All right. Well, let's stop there. And the first quiz is a week from today. Okay, so be sure that you're reading through the notes and getting ready for the quizzes.